In part A, we determine the intervals when the population is increasing using the derivative of the population function. So here we have the derivative of the population function, that is dp by dt equals 4 by 500 times p times 5 minus p for p greater than 0. So to find the interval where the population is increasing, basically we have to find the critical point of the population function and prepare sign chart using the critical points, and then determine according to the sign chart. Whenever the first derivative is greater than 0, we say it is an increasing interval, and in intervals where the first derivative is less than 0, we see that the population is decreasing. So let's find the critical point of this population function. For this, we have to set the first derivative equals 0 and solve for p. So I'm going to set the dp by dt equals 0 and solve for p. So therefore we have 0 equals 4 by 500 times p times 5 minus p, and this equals 0. So solving for p, we get either p equals 0 or 5 minus p equals 0. And so this gives p equal to 5, and here we get p equal to 0. That is, these are the two critical points of the population function. So using this critical points, let's prepare the sign chart. So we can put this sign chart using the number line. So I put this p equal to 0 and this one p equal to 5. And we can see that we have three intervals over here. However, since p is always greater than 0, we consider only the interval, that is between 0 to 5 and greater than 5. So basically, we have to find the sign of the population of the derivative function in these two intervals. This is for the dp by dt. So let's use the dp by dt. This equals 4 by 500 times p times 5 minus p. Now let's consider any random value between the in the interval 0 to 5. Say for example I consider 4 and plug it into this equation. So I get 4 by 500. I plug in p equal to 4, and this one is 4. I'm sorry, this one is 5 minus 4. So it's 5 minus 4. Basically, we need to understand the sign. This quantity is positive, this 4 is also positive, and 5 minus 4 is 1, which is also positive. So basically, this is greater than 0 in the interval 0 to 5. So let's mark this as a positive interval between 0 to 5. Now let's consider some random values in the interval 5 to infinity. So I'm going to consider p equal to 6 and plug it into the derivative function. So when I do that, I get 4 by 500 times 6 times 5 minus 6. This is positive, but this is negative. So overall product of a positive and negative is a negative, and that means it is less than 0. So in the interval 5 to infinity, the derivative function is negative, which means it is a decreasing interval. So here we see that the population function is decreasing because it is negative, and in this interval 0 to 5, the population function is increasing because the derivative is positive in this interval, and that means we can write down the increasing and decreasing intervals for the population function. So let's answer the part A. The population is increasing when the increasing interval is 0 to 5. So we write down that as p greater than 0 and less than 5. Now let's answer part B. And here we have to write down the decreasing interval for population. So we write population is decreasing when p is greater than 5. So here we write p greater than 5. So we have identified the increasing and decreasing intervals of population. In part C, we determine P of 50 using the initial condition P of 0 equals 3. So for that, basically we have to solve this differential equation so that we get P of t. Once we know P of t and also identify the constant of the integration using this initial condition, we can determine P of 50. So let's focus on solving this differential equation. So this one is a first order differential equation which can be solved by separation of variables method. We are going to solve by separation of variables. So first I'm going to separate the p variables. So for that I'm going to divide both sides by this expression. And so when I do that, I get 1 by p times of 5 minus p times dp by dt, and this equals 4 by 500. Now I multiply both sides by dt, so that on the left side I will be left with dp over p times 5 minus p, and this equals 4 by 500 times dt. Now to solve for p, we integrate the both sides because we have separated the variables. If you can see here, on the left side we have separated the p variables, and on the right side we have separated the t variables. So let's integrate both sides so that we can solve for p. And basically we have to integrate this using method of partial fractions, which we will do. And integration of this one equals, we can factor out the 4 by 500 out of the integral, and then we just have dt. So therefore this gives the constant remains the same. And then integral of dt is basically 1 dt. Integral of 1 dt is t. We also put the constant of integration, which is c1. So we have integrated the right side expression, which is this expression. Now let's use the method of partial fractions to integrate this left side expression. So I'm going to consider the rational expression 1 by p times of 5 minus p. First, we are going to write down this as a sum of partial fractions. So I'm going to simplify this by factoring out the negative from this expression and transferring the negative to the negative to the 1 in the numerator. So therefore, this will become negative 1 divided by p times of p minus pi. Otherwise, we rewrite this into this form so that it will be convenient when we use the partial fraction method. And so this can be written as, according to the partial fraction method, this one is a divided by p plus another constant b divided by p minus pi. Now we multiply both sides of this equation. This is the equation that we are going to work on. We multiply both sides of this equation by this p times of p minus pi, which is a common denominator. And when we do that, on the left side, we are left with negative 1. And this equals, on the right side, we'll be left with a times of the factor which it doesn't have in the denominator. So here we have the denominator p, but the common denominator is p times of p minus pi. That is, when you multiply a by p with this expression, this p and this p will get cancelled, leaving us a times of p minus pi. And similarly, this constant b will get multiplied with only p. Now to solve for a and b, we can substitute some random values for p. So first, let me plug in p equal to 0 on both sides. This side is independent of p, so it's going to be negative 1, and this equals a times of, we are plugging p equal to 0, so it is 0 minus 5 plus b times of 0. This case cancel because b times 0 is 0, and this one reduces to a times of negative 5 is negative 5a, and this equals negative 1. Solving for a, we get a equals negative 1 divided by negative 5, which equals a positive 1/5. So we have determined the value of a, which is 1/5. Now let's determine the value of b by plugging in p equal to 5 into the same equation. So we'll be getting negative 1, and this equals a times of, I'm plugging p equal to 5, so therefore this becomes 5 minus 5 plus b times of 5. And so this one 5 minus 5 is 0, so therefore this becomes 0. And here we get negative 1 equals b times of 5, which is 5b. Solving this, we get b equals negative 1/5. So we have determined the values of a and b as this one. This means we can write down the rational function by substituting the values of a and b over here. And so let's consider the left side expression of the integral. The left side of the integral, we have dp divided by p times of 5 minus p. And this we have written as negative 1 times negative 1 divided by p times of p minus 5 dp. This is integral. We will not have to put this dot. And this we have split this into two fractions, that is integral of a divided by p plus b divided by p minus 5, where a equals 1/5. So I plug 1/5 for a, this divided by p, plus b is negative 1/5, and this divided by p minus 5. And this is we have to integrate with respect to p, that is dp. So this can be written as sum of two integrals, that is the first integral will be 1/5 divided by p dp, wherein I factor the 1/5 constant and then write down this as 1 over p dp. And then second integral we have negative 1/5, so this becomes negative 1/5. I factor out the negative 1/5, and then I write down only the rational expression 1 over p minus 5 dp. Now we can integrate this according to the standard integral formula. This will be natural logarithm of p, absolute value of p, minus this will be negative 1/5 natural logarithm of p minus 5. So in the next step, we can factor the 1/5 and write down this as a single natural logarithm. That is, if we factor 1/5, we'll be left with natural logarithm of absolute value of p minus natural logarithm of absolute value of p minus 5. Now we use the property of natural logarithm, that is natural logarithm a minus natural logarithm b. This is basically the difference of natural logarithm, which equals natural logarithm of a over b. So we will use this property. So according to this, this will be 1/5 of natural logarithm of the first one is p divided by p minus 5. We put this using absolute value. So this is the result of the left side integration, and this equals this right side result. So let's equate both of them now. So therefore we can write down 1/5 of natural logarithm of p over p minus 5 absolute value, and this equals 4 by 500 t plus c1. We write down this as 4 by 500 t plus c1. We will now solve for t from this equation. So first I'm going to multiply both sides by this constant 5, so that we remove the fraction on the left side. And so when we do that, we get natural logarithm of p over p minus 5, and this is an absolute value, and this equals, we multiply the right side expression by 5, that is 5 times of 4 by 500 t plus c1. And when we distribute this 5 into the first term, we get 5 times of 4 by 500, that is 5 times of 4 by 500. Can simplify this to 500 goes in 5 as 100 times, and 4 goes into 100 as 25 times. That is, this one is basically 1 by 25, and we also have a t, so therefore this becomes t by 25, plus 5 times of c1 is basically a constant, so we can put this as constant once again as c1. And here on the left side we have natural logarithm of p over p minus 5. Now let's raise both sides to the e. so that we can solve for p. So here we raise to the e, and here also we raise to the e. And this e and natural logarithm both are inverse, so they cancel out each other, and leaving us p divided by p minus 5. And this equals e raised to the power of t by 25 plus constant c1. Now let's simplify the right side expression. This e raised to the power of t by 25 plus c1, basically we can rewrite this as e raised to the power of t by 25 times e raised to the power of c1. This is according to the exponent clause. And this one, e raised to the power of c1, is going to be another constant. We can let e raised to the power of c1 as a constant, that is capital C. And thus the right side expression gets simplified to c times of e raised to the power of t by 25. And on the left side, we have p divided by p minus 25. Now let's reciprocate both sides so that we can solve for p. And doing that, we get p minus 5 divided by p. And this equals 1 over c times of e raised to the power of t by 25. And thus the left side expression can be written as p by p minus 5 by p, and this equals 1 over c times of e raised to the power of t by 25. And this reduces to p by p is 1 minus 5 by p, and this equals 1 by c e raised to the power of t by 25. Now we can add this to both sides, and so when we do that and also subtract this from both sides, we get a 1 minus 1 by c times of e raised to the power of t by 25. This equals 5 by p. Let's simplify this further. This equals, I'm going to write down this 1 by c e raised to the power of t by 25 as 1 by c e raised to the power of negative t by 25, and this equals 5 by p. Now we can consider this 1 by c as another constant. Let's say this pa. So therefore we can write this equation as 1 minus a times of e raised to the power of negative t by 25, and this equals 5 by p. We multiply both sides by p, we get p times of this quantity, that is 1 minus a e raised to the power of negative t by 25, and this equals 5. Now we divide both sides by this expression to solve for p. So therefore we write p, and this equals 5 divided by 1 minus a e power negative t by 25. So basically this one is the p of t. So this is the expression or the solution of the differential equation. P of t equals 5 divided by 1 minus a e power negative t by 25. We now use the initial condition p of 0 equals 3 so that we can determine the constant a. So let's plug in t equals 0, and when we do that we get p of 0, this equals 5 divided by 1 minus a e power t is replaced as 0, so this becomes negative 0 divided by 25, and this p of 0 equals 3. So replace this by 3. This equals 5 divided by, this one is e power 0, which is 1. So it is 1 minus a. Multiplying both sides by 1 minus a, we get 1 minus a times 3 equals 5. Or otherwise, we solve for 1 minus a equals 5 thirds. We now subtract 5 by 3 and add a to both sides. And when we do that, we get 1 minus 5 by 3, and this equals a. And so solving for a, we get a equals 3 minus 5 divided by 3, which is negative 2 thirds. So we have determined the constant a equals negative 2 thirds. And this means we can substitute into the solution p of t. So let's rewrite p of t by substituting this one. So therefore we write p of t, and this equals 5 divided by 1 minus a. A is negative 2 thirds, e raised to the power of negative t by 25. So this can be simplified as 5 divided by 1 plus 2 thirds e power negative t by 25. So this is the expression for p of t after we have solved for a, or we have determined the constant a. Now we have to determine p of 50. We have to plug in t equal to 50 and find the population when t equals 50. So we get p of 50, and this equals 5 divided by 1 plus 2 thirds e raised to the power of negative 50 divided by 25. And working out this out, and we get 4.586. This is approximated to three decimal places, and when rounded to the whole number we can approximate this to 5. So p of 50 is approximately 5.